In this video, we're going to talk about the formulas of compounds and how we know things like water are definitely two H's for each O. So in the objectives, we're going to determine how many atoms are in a compound and how many molecules or compounds are in a reaction, as well as explain the laws of definite and multiple proportions. So subscripts that you are going to see in these formulas are the little number following an element symbol. They indicate the number of atoms of only that element in the compound. For example, H2O means there's two H atoms for every one O atom. In CO2, there's one implied carbon atom for every two oxygen atoms. So we don't really write ones unless you really want to. You could write H2O1 or C1O2. We assume that it has to happen at least once if we're writing it. And all other numbers should be written to tell us how many we're drawing. So like when we draw H2O, we draw two H's for each O, and we draw one carbon for each O2. Now I don't care if you know that they're going to actually catty corner HOH and OCO. If you wrote HHO for now, that's fine. The big numbers that you might see in formula are coefficients, just like you see 3x in math and you call the 3 a coefficient. It indicates the number of molecules or compounds there are in an example. So for a 3H2O, there are 3 molecules of water. And that means you're going to draw 3 separate waters. Each one of those waters is going to have 2 H's for every O. So H2O, 3 times H2O, H2O. So for example, how many atoms of hydrogen are indicated by 2 waters? So that means there would be 2 water systems, and there are 4 H's, 1, 2, 3, 4. But another way to do it is just to distribute the 2 through the water and say that there are 2 times 2, or 4 hydrogens, right? You could also do it for oxygen. You can count them, or you can just distribute through 2 times 1, and there's 2 O's, right, as we drew. So how many molecules of water are represented by 2 H2O? Remember, molecules when they're combined, so it's just 2 molecules of water, but the atoms are the smaller parts that you're drawing. The first law we're going to talk about is the law of multiple proportions. It says when 2 elements react to form more than one compound, a fixed mass of one element will react with a fixed mass of another element in a ratio of small whole numbers. In English, what it means is you're going to get things like H2O and not H1.5O17.2, and you're always going to get the same thing, H2O, or some rendition of it. So it's going to be whole numbers. What we're going to do is we're going to do an example that's on page 12 of your packet. This will help all students understand how to do that page. So I would recommend taking out page 12 of your packet and writing down these answers as you go. You might want to pause the video to go get it out, so that way you have it done. Okay, in the packet it says that compounds of carbon and oxygen can form. Sometimes when they form, 57.1 grams of oxygen react with 42.9 grams, so that's done in a lab to see exactly what the ratio is. And in compound B, a different time that C's and O's react, it was 72.7 grams of oxygen reacting with 27.3 grams of carbon. So the first thing they want us to do is determine the value of the ratio of mass of oxygen divided by mass of carbon. So in compound A, we would do 57.1 grams or mass of oxygen divided by the mass of carbon, 42.9. And when you solve that, you're going to place that in the blank here, which comes out to be, I think, 1.33. We'll do the same thing for compound B, so it'll be the oxygen on top divided by the carbon on the bottom. And yes, you should show your work on your packet, and then show your answers in the blanks. So then the first time we did it, it came out to be 1.33, as I mentioned. And when you do in your calculator 72.7 divided by 27.3, we get 2.66. The next question asks you what the ratio of that looks like. So if you're taking those numbers and they ask you the ratio is, you're going to say that the B is twice that of A, right? Literally 2.66 is double 1.33. Next, they ask you to explain those improper fractions. So taking 1.33, what that means is, what would that be if you were, is it 4 halves, right? Like what's the value of 1.33? So I thought that, and most people know that this is divided by 0.33, like this is a multiple of 0.33. It happens in the number 1, 0.33 goes into 1 3 times, and then there's another 0.33. So this is actually the same fraction as 4/3, right? It's 1 1/3 or 4/3. Thinking along that same line, if you have 2.66, the improper fraction that 2.66 came from was double 4.4/3 or 8/3, because it was 2 wholes and a 2/3, which is 3/3, 3/3, and 2/3 or 8/3. So this is just a review of math skills. If you're not quite sure what's going on here, we'll do them again in class, or you should come to a Google Meet. So what does this mean? So I'm just recopying it up here. that in compound A, there were four oxygens for every 3 carbons. And so the carbon we're going to represent it as red. And in B, there's 8 grams of oxygen for every 3 grams of carbon. So we're going to represent oxygen as white. And in hypothesis 1, this is what scientists were thinking. What does this mean? If this is how they're reacting, 4 grams of oxygen for every 3 grams of carbon, 8 grams of oxygen for every 3 grams of carbon, that either means the particles of C and O have the same mass, or that O is heavier than C. So let's see what both hypotheses. If C and O have the same mass, that means that they're in compound A, there are 4 oxygens for every 3 carbons, because of the same mass. Right, so the oxygens are white and the carbons are red. And then it means in compound B, there would have to be 8 oxygens, so 8 whites for every 3 carbons, or 3 reds. And these would be their compounds. This is what they would look like. In hypothesis 2, if the particles of O are just heavier than carbons, then that means that 4/3 of O over C, we would just say maybe O weighs 4 and C weighs 3. So in that case, I would say that they just have oxygens that weigh a little bit more, so maybe their particles just a little bit bigger. And carbon weighs a little bit smaller, so maybe its particles just a little bit smaller. And in that case, in the second compound, if oxygen weighs 8 instead of 4, then maybe that just means there's twice as many oxygens. And so that would be drawing 2 of those whites. I'm sorry, twice as many oxygens. It should be, hold on. All right, so this should be fixed, sorry. So there should be 2 whites for every red carbon, right? So there it is. So the way that we looked at this, there has to be do we think it's this complicated, or do you think it's just as simple that maybe that each gas is slightly different mass based on different properties? And because of that, this ratio makes a little bit more sense. These are actually things we know, right? Carbon monoxide, from carbon monoxide poisoning, carbon dioxide, the stuff we blow out of our mouths, right? So this makes a little bit more sense than I don't know what these things are. I've never heard of C3O4 or C3O8, but we've heard of these 2 things. So hypothesis 2 makes more sense, that now we're realizing that each particle maybe has its own mass and they're slightly different from one another, and they react in fixed positions, so either as CO or CO2, whole numbers. And then the second law is a law of definite proportions, that a given chemical compound always contains the same elements in the exact same proportions by mass. For example, CO2 is always going to be 1C for every O2, every time you see it. If you see CO3, that's an entirely different substance. So an example of the type of questions we'll be doing on later pages is table sugar is a compound known as sucrose, and sucrose is composed of the elements carbon, hydrogen, and oxygen. Analysis of 20 grams of sucrose from a bag of sugar finds that the sugar is composed of 8.44 grams of carbon, 1.3 grams of hydrogen, and 10.26 grams of oxygen. Now recognize, if we added those together, that would be the 20 grams of sucrose. Expressed as fractions, the ratio of each mass of each element to the total mass. So what we're going to do is say that the carbon was 8.44 out of a total of 20. The hydrogen was 1.3 out of a total of 20. And the oxygen was 10.26 out of a total of 20. Taking those numbers, we're going to talk about percent composition by mass. So all we have to do to find a percent is to literally divide those numbers that we just got in the previous question, which I listed all here, and then times by 100. These will give us percentages of how many carbons, hydrogens, and oxygens are in the physical sample every time. Whether you have 20 grams or you have 40 grams or 100 grams, there will always be 42% of carbon, 6.5% of hydrogen, and 51% of oxygen. And that's a definite proportion. It will always be that percentage. And therefore, eventually we'll figure out what sucrose formula is, which we'll get to in class. So that will remain the percent composition of each element in any sample, whether it's 20 grams or 4 grams of sucrose. At this point, you should be able to determine how many atoms are in a compound and how many molecules or compounds are in a reaction, as well as explain the laws of definite and multiple proportions.